There is a building in Cleveland, Ohio, with a machine inside it that is taller than the building looks from the road. Most of it is underground. Above the floor, it stands about 87 feet, roughly an 8-story structure of steel columns and crossheads painted in industrial gray, weighing around 8,000 tons all by itself. It does not move quickly. When it works, it closes with the patience of a geological event, squeezing a glowing billet of aluminum or titanium between two steel dies with a force of 50,000 tons. There is no noise of impact. There is a hiss, a groan of hydraulics, a slow settling. And when the dies open again, a piece of metal exists that could not have existed anywhere else in North America an hour earlier. That machine began operating on the 5th of May, 1955. It has been in near continuous service ever since. It is not a museum piece, not a preserved relic with a plaque and a rope around it, although it does have a plaque, designating it a historic mechanical engineering landmark. It is a working tool. Parts formed on it, or on its near-identical twin in Massachusetts, are flying over your head right now. Inside the wings and landing gear and structural spines of aircraft designed decades after the press itself was built. And it is one of 10. 10 machines commissioned by the United States Air Force, built between the end of the Second World War and 1957, at a total cost of $279 million in the money of that era. 4 of them were forging presses. 6 were extrusion presses. Together they were called, with the flat bureaucratic honesty of the period, the heavy press program. The claim that 10 machines decide what shape an airplane can be sounds like exaggeration. It is closer to arithmetic. To understand why, you have to understand what a forging is, and why an aircraft cannot simply be assembled out of whatever pieces a designer draws. Metal has a grain. Not the visible grain of wood, but an internal structure of crystals, elongated and aligned by whatever process shaped the part. If you take a thick plate of aluminum and machine away everything that is not the part you want, you get the correct geometry. But the grain of that plate runs the way the rolling mill left it, straight and flat, indifferent to the curves and load paths of the component you carved out of it. Wherever your part turns a corner, the grain runs out into the surface. Those exposed grain ends are where fatigue cracks like to start. And in an airframe, fatigue is not an inconvenience. It is the thing that kills people 20,000 flight hours after everybody who designed the aircraft has retired. Forging does something different. It takes a heated billet and forces it to flow into the shape of the die cavity. The grain flows with it, curving where the part curves, running continuously around corners and through fillets, following the load paths instead of cutting across them. A forged part of the same alloy and the same geometry as a machined one is stronger where it matters, and much more tolerant of cyclic loading. That is why the most critical structures in an aircraft, the bulkheads that carry wing loads into the fuselage, the beams that carry the entire mass of the airplane through the landing gear and into the runway at touchdown, are forged, not carved. So the question becomes, how large a forging can you make? And that question has a brutally simple answer, one that any process engineer can do on the back of an envelope. Forming metal in a closed die requires a certain pressure across the entire projected area of the part, the area you would see if you looked straight down at it through the press. For aluminum alloys, that pressure runs on the order of 20 to 40 tons per square inch, depending on the alloy, the temperature, the complexity of the shape, and how sharply the metal has to flow into thin ribs. For titanium, it can be half, again as much or more. Multiply the area by the pressure, and you get the force the press must deliver. If the press cannot deliver it, the metal does not fill the die. You get a part with unfilled ribs, cold shuts, folds, a piece of scrap that took 4 hours to heat and cost the price of a small car. Run the numbers on 50,000 tons. In aluminum, at the friendlier end of the pressure range, you can fill something like 15 or 16 square feet of projected area in a single piece. In titanium, considerably less. Those numbers are the outer boundary of a monolithic aerospace forging in the United States. Everything larger has to be split into 2 parts and joined, with fasteners, which means holes, which means stress concentrations, which means added weight, added assembly hours, added inspection intervals, and added failure modes. This is the sense in which a machine decides shape. A designer sits down with a structural layout for a fighter's mid-fuselage. She would like one continuous bulkhead carrying the wing carry-through loads. Whether she can have it depends on the projected area of the part, the alloy, and a number that was fixed in the early 1950s by a contract between the Air Force and a machine builder in Pennsylvania. If the number works, the aircraft gets a single piece of titanium doing the work. If it does not, the aircraft gets a joint, and every kilogram and every inspection that joint implies, for the entire service life of the fleet. The story of how those numbers came to be fixed begins, as so much of post-war American industry does, in the rubble of Germany. During the Second World War, German industry had pushed die forging further than anyone else. The Reich was chronically short of the alloying metals that make high-strength aluminum, and it had comparatively abundant magnesium. Magnesium is light, but it is unpleasant to work. It does not like to be hammered, and it forms much better under slow, sustained pressure than under impact. That pushed German engineers toward very large hydraulic presses at a time when American practice still leaned on drop hammers. Machines that beat metal into shape with falling weight, rather than squeezing it. By the end of the war, Germany operated the largest die forging presses in the world. When Allied technical intelligence teams went through the plants in 1945, they found machines of a scale that had no American equivalent, and they found the parts those machines had produced. Large, complex, single-piece aircraft components that American manufacturers would have had to build from several pieces riveted together. Then came the division of the spoils. The largest surviving German press, a machine in the range of 33,000 tons, went east, dismantled, and shipped to the Soviet Union as reparations. The United States came away with a pair of smaller machines on the order of 16,500 tons each. In the arithmetic of who ended the war holding the biggest press, America finished second and knew it. For a few years, that hardly seemed to matter. Then, it mattered enormously. The Soviet Union tested a nuclear device in 1949. In 1950, the Korean Peninsula went to war. The American aircraft industry was being asked to move within a single decade from propeller-driven aircraft of aluminum sheet and rivets to swept-wing jets flying near and beyond the speed of sound. Aircraft with thin wings that left no room for deep built-up structure. Aircraft with concentrated loads that demanded thick, strong, precisely shaped structural members. Thin wings and heavy loads are exactly the combination that forces you toward large forgings, and the country's capacity to make large forgings was, by the measure of what had just been found in Germany, second-rate. The response was a program of state industrial planning, of a kind Americans generally prefer not to describe as state industrial planning. The Air Force would pay for the presses. The Air Force would own the presses. Private companies, Alcoa, Wyman Gordon, Kaiser Aluminum, Curtiss-Wright, the Harvey Machine Company, would house them, staff them, and run them under contract on government land or government-designated plant sites. Some of the installations carried Air Force plant numbers. The Cleveland site was Air Force Plant 47. The original plan was ambitious to the point of implausibility. 17 presses, at an expected cost approaching $390 million. Studies and arguments and budget cycles ground that down. In 1953, the program was cut back to 10 machines. The work of building them ran through the mid-1950s, and the last of them came online in 1957. 4 of the 10 were forging presses, and they were the giants. 2 were rated at 50,000 tons. The first, built by Mesta Machine Company of West Homestead, Pennsylvania, went into Alcoa's Cleveland Works and made its first production stroke in May 1955. The second, built by Lowy Hydropress, went to Wyman Gordon in Grafton, Massachusetts, and began operating in October of the same year. 2 more, rated at 35,000 tons, were installed alongside them. One at Alcoa in Cleveland, built by United Engineering. One at Wyman Gordon in Grafton, built by Lowy, running from February 1955. The remaining 6 were extrusion presses, machines that push a heated billet through a shaped die to produce long structural sections, the spars, stringers, longerons, and rails that run the length of a wing or a fuselage. A 13,200-ton Schliemann extrusion press went to Alcoa in Lafayette, Indiana in 1953, a German-built machine which tells you something about who the world's acknowledged experts were. 2 8,000-ton Lowy extruders went to Kaiser Aluminum at Halethorpe, Maryland. Harvey Machine Company in Torrance, California received an 8,000-ton machine and later a 12,000-ton Lombard press that came on stream in August 1957. Curtiss-Wright in Buffalo, New York took a 12,000-ton Lowy extruder, which would later be moved to Texas. 10 machines, all of them ordered, designed, and commissioned before 1958. The construction itself was an exercise in moving things that do not want to be moved. The largest castings and weldments for these presses were among the heaviest single pieces of machinery ever transported over American roads and rails. Routes had to be surveyed for bridge capacity and clearance. Special rail cars were built. Foundations went down deep enough that a substantial fraction of each press lies permanently below floor level, its lower structure and hydraulic accumulators buried in reinforced concrete, because the reaction forces have to go somewhere, and the somewhere is the ground. The Cleveland press gives a sense of the scale in numbers rather than adjectives. Its die table, the working surface between which parts are formed, measures roughly 26 feet by 12. Its maximum stroke is about 6 feet. Its total mass is around 8,000 tons, and its full height above the floor approaches 90 feet. It is a building that happens to be a machine. What did the country get for $279 million? It got first a step change in what an American airframe could be made of. Parts that had been assemblies of dozens or hundreds of smaller components, joined by thousands of rivets, could now be single pieces. Weight came out, assembly labor came out, inspection burden came out. Reliability went up because a joint that does not exist cannot fail. It got, second, a strategic capability in titanium. Titanium is the metal of high-speed flight. It holds its strength where aluminum softens, and it does not weigh what steel weighs. It is also miserable to forge. It requires higher pressures, tighter temperature control, and dies that will survive conditions that destroy ordinary tooling. The heavy presses arrived at almost exactly the moment the American aerospace industry needed to learn titanium at scale, and they were the machines on which that learning happened. The large titanium bulkheads of the F-15, the members that carry the wing loads through the fuselage of an air superiority fighter designed in the late 1960s, came from this program's presses, 15 years after those presses were built. It got third, something nobody put in the justification memoranda, a permanent constraint. Because once the machines existed, everything designed afterward was designed to them. This is the quiet mechanism by which industrial infrastructure shapes engineering. No one at Boeing or Lockheed or McDonnell Douglas ever received a memo saying, "Your bulkhead may not exceed the following projected area." They did not need one. The forging supplier's capability sheet said what it said. The manufacturability review asked whether the part could be made. The answer depended on a press installed before the designer was born. Over decades, across hundreds of programs, that constraint quietly selected which structural concepts survived contact with reality, and which quietly disappeared from the drawings before anybody outside the company ever saw them. The economics ensured the constraint would hold. A press of this class is not simply expensive. It is expensive in a way that no single aircraft program can justify. The machine outlives its buyer's business plans by half a century. Its cost cannot be amortized against one fighter or one airliner, because the fighter and the airliner will each be finished long before the press is worn out. Only something with a longer time horizon than a corporation, a government, preparing for a war it hopes never to fight, writes that check. The Air Force wrote it once, in the 1950s. For 60 years, nobody in the United States wrote it again. So the ownership arrangement persisted with the strange durability of things that work. The presses remained government property, operated by private firms for decades after the emergency that produced them had faded into history. Eventually, the Air Force divested them to the companies that had been running them all along, and the machines passed into private hands. But the underlying fact did not change. The 4 heavy forging presses stayed where they had been installed, in Cleveland and in Grafton, doing what they had been built to do. Not all 10 survived. The extrusion presses had a harder time of it, because extrusion capacity is more fungible, and the plants that house them were more vulnerable to the ordinary attrition of American manufacturing. The Harvey machines in Torrance were scrapped, one in the 1990s, one a few years earlier. The Kaiser presses at Hallethorpe, Maryland were finally scrapped in 2021, 66 years after they were installed. The Curtiss-Wright machine left Buffalo for the Gulf Coast, but the 4 forging presses, the 50,000-ton pair and the 35,000-ton pair, are still running. So is the Schloman extruder in Indiana. Roughly half the program is still in production 7 decades on, which is not a normal outcome for capital equipment of any kind. There is a moment in the recent history of the Cleveland press that captures the whole logic. In the years after 2010, demand for large aerospace forgings rose sharply. New wide-body airliners, new fighter programs, a global fleet expansion. The press had been idled. Its owner faced a straightforward choice: build a new machine or restore the 1955 one. They spent a very substantial sum, reported in the tens of millions of dollars, on refurbishing hydraulics, controls, and structure, and put the old press back to work. Rebuilding a machine older than the jet airliner was the cheaper, faster, lower-risk path. That tells you what building a new one would have cost. Eventually, somebody did build a new one. In October 2018, in Paramount, California, a company called Weber Metals, part of the German group Otto Fuchs, inaugurated a 60,000-ton closed-die forging press supplied by SMS Group in a project valued at around $180 million. It is a pull-down design, mounted in a pit, and at the time of its opening it was described as the most powerful press of its type in the world. It is the first machine to exceed the heavy press program's capability on American soil. and it arrived 63 years after the Cleveland press made its first stroke. Elsewhere, the ceiling moved sooner. Russia inherited the German press and kept going, building enormous die-forging capacity of its own. France operates heavy presses in the same class. And in April 2013 in Deyang, Sichuan province, the China National Erzong Group brought an 80,000-ton die-forging press into trial production, a machine over 40 meters tall, designed and built domestically. The list of countries operating die-forging presses above 40,000 tons is short enough to recite: China, the United States, Russia, France. That list is not a curiosity. It is a map of who can independently make the largest single-piece structures in a modern aircraft, and therefore, who can independently design one without asking permission. Everything downstream of those machines, the fighter's bulkhead, the airliner's landing gear beam, the engine's largest rotating parts, is gated by a small number of installations, most of them decades old, all of them essentially impossible to replicate quickly. A country can design an aircraft on a computer in a year. It cannot conjure a 50,000-ton press in a year or 5 years, and it cannot borrow one, which brings the story back to the shape of the aeroplane. It is tempting to believe that aircraft look the way they do because of aerodynamics, because air behaves in certain ways at certain speeds, and the shapes we see are the answers to that physics. That is true, and it is incomplete. Aerodynamics tells you what shape you would like. Manufacturing tells you what shape you may have. The gap between those two things is where engineering actually happens, and it is filled with constraints that have nothing to do with airflow. What a die can fill, what a machine tool can reach, what a press can close on, what an inspector can certify. Of those constraints, the press is among the most absolute because it is the least negotiable. You can hire more machinists, you can requalify an alloy, you can redesign a fastener pattern. You cannot argue with 50,000 tons. Either the force is sufficient for the projected area, or the metal does not fill the die, and no amount of schedule pressure or executive attention changes that. So, the shape of a modern airframe carries, embedded in it, a set of decisions made in Washington and Pennsylvania and Cleveland between 1950 and 1957. By people responding to the discovery in a bombed-out German factory that somebody else had learned to squeeze metal harder than they had. They built 10 machines. They spent what would today be several $billion. They wrote no design rules and issued no guidance on aircraft configuration. They simply established, physically and permanently, the outer boundary of the possible. Every generation of American aircraft since has been drawn inside that boundary. The engineers doing the drawing mostly do not think about it any more than a novelist thinks about the width of the page. It is not a limitation they encounter. It is the shape of the space they work in. And the machines are still there, in Ohio and in Massachusetts, closing slowly on glowing metal, holding for a few seconds, opening again. Older than the aircraft they make parts for, older than nearly everyone who works around them. Still setting, one stroke at a time, the terms on which an airplane is allowed to exist.